Industry skills, practical knowledge, real-world impact. This is SimpleGyan.
Every year, more than 1 billion tyres reach the end of their useful life. They are tough, bulky, non-biodegradable, and extremely difficult to dispose of safely. For decades, many waste tyres were burned, dumped, or used only as low-value fuel. But hidden inside every waste tyre is something extremely valuable. A black engineered material that gives tyres strength, abrasion resistance, UV protection, and long service life. That material is carbon black. Today, industry is trying to solve two problems at the same time: waste tyre pollution and carbon-intensive carbon black production. And the solution may come from an unlikely source: the black solid residue left after tyre pyrolysis. Waste tyre char upgraded into recovered carbon black, or RCB. This is the engineering story of how waste tyre char can be converted into high-grade commercial carbon black for rubber, plastics, coatings, inks, and future low-carbon industries. Carbon black is one of the oldest industrial materials known to humans. Long before modern chemical plants, people collected soot from burning oils, resins, and lamps. This material, called lamp black, was used in inks, paints, and writing materials. But the true industrial revolution of carbon black began when rubber engineers discovered something extraordinary. Plain rubber was soft, weak, and wore out quickly. But when fine carbon black particles were mixed into rubber, the material became stronger, tougher, and more resistant to abrasion. This changed the tyre industry forever. By the early 20th century, carbon black became one of the most important reinforcing fillers in rubber. Later, the oil furnace process, developed in the 1940s, became the dominant route for producing modern carbon black. Today, furnace black accounts for more than 95% of global carbon black production. Modern carbon black is produced by partial combustion of hydrocarbon feedstocks. In a furnace reactor, temperatures reach up to 1,800 degrees Celsius. This process is powerful and highly controlled, but it is also fossil feedstock based. And that is where industrial decarbonization begins. A tyre is not just rubber, it is a highly engineered composite. Inside, you find rubber polymers, steel wire, textile cord, sulfur, and zinc oxide. Carbon black typically forms about 20 to 40% of tyre weight. So when a tyre reaches end of life, the carbon black inside it is not destroyed, it is locked inside a complex rubber matrix. The engineering challenge is simple to say, but difficult to execute. How do we separate and upgrade that carbon-rich material without burning the tyre? The answer is pyrolysis. Pyrolysis means heating organic material in the absence of oxygen. In normal burning, oxygen produces flame and smoke. But in pyrolysis, oxygen is excluded. The tyre does not burn. Instead, heat breaks long rubber polymer chains into smaller molecules. The process produces three major product streams: pyrolysis oil, non-condensable gas, and solid carbon-rich residue, recovered carbon black char. Tyre pyrolysis commonly produces around 35 to 48% solid RCB fraction. For a simplified mass balance, from 1,000 kilograms of processed waste tyre, a plant may produce approximately 350 to 400 kilograms of recovered carbon black char, along with oil and fuel gas that can power the reactor itself, improving energy efficiency. Raw tyre pyrolysis char is a complex material. It contains recovered carbon black, but also inorganic ash like zinc and silica, residual hydrocarbons, and coke. A major difference is ash content. Conventional carbon black has ash below 0.5%, while raw RCB can contain 10 to 20% ash. The industrial process begins with Stage 1, tyre collection and sorting, removing oversized contamination. Stage 2 involves shredding tyres into chips and using magnetic separators to remove steel. Uniform particle size is critical for stable heat transfer. Stage 3 is drying and feed preparation, as moisture is the enemy of stable pyrolysis. Stage 4 is the reactor, often a rotary kiln or auger reactor. Typical tyre pyrolysis is carried out between 425 and 600 degrees Celsius, cracking rubber into vapours. Stage 5 involves vapour handling and condensation to recover oil and gas. In Stage 6, the solid char is cooled in a sealed inert atmosphere. If the hot char contacts air, it can oxidise or ignite, making this a critical safety stage. Stage 7 is grinding. Raw char particles are large and irregular. Milling reduces size and breaks agglomerates. A modern plant targets a specific particle size distribution to ensure good dispersion in rubber and plastics. Stage 8 is demineralization, one of the most important steps. Chemical treatment, like acid washing, is used to remove mineral ash and sulfur. This transforms low-value char into a serious industrial raw material. Stage 9 involves thermal upgrading and activation. Secondary thermal treatment under nitrogen, steam, or CO2 removes volatile residues and modifies the surface area. The plant must balance surface area and structure for the final market. Finally, stage 10 is pelletization and packaging. Carbon black powder is dusty and messy. Pelletization creates high-density, low-dust pellets that flow well and disperse properly during rubber mixing. High-grade RCB is defined by measurable properties: ash, sulfur, BET surface area, and OAN structure. ASTM formed Committee D36 in 2017 to develop global standards, ensuring consistency for industrial customers. Recovered carbon black helps decarbonization in 3 ways: reducing fossil feedstock reliance, converting waste into material, and supporting circular economy goals. Michelin states that RCB can reduce CO2 emissions by over 90% compared to virgin carbon black. The road to high-grade RCB has challenges: feedstock variability, ash content, and organic residues. Engineering solutions like feedstock sorting, demineralization, and thermal upgrading are essential for commercial qualification. A commercial RCB plant is a complex integration. It is a chemical process plant, a powder processing plant, a wastewater treatment system, and a materials engineering laboratory, all working together. High-grade RCB is used in tyre sidewalls, conveyor belts, plastic masterbatch, and inks. While tyre tread reinforcement remains the most demanding application, RCB is becoming a predictable engineering material for the global market. The future depends on innovation, better reactor control using digital twins, low chemical demineralization, and renewable energy integration. The next industrial revolution is about recovering the carbon we already produced. A waste tyre is a concentrated carbon resource. Through advanced chemical engineering, we turn a waste problem into a manufacturing opportunity. The black powder that once strengthened the tyre returns again, not from crude oil, but from the tyre itself.